Welcome to this lecture on transform methods in network analysis. In this lecture, we are going to look at the use of Laplace transform to solve network analysis problems. As we already know, the Laplace transform of a function f of t is defined as integral 0 minus to infinity f of t e to the power minus st dt, and it is denoted by capital F of S. S is the complex frequency given by sigma plus j omega, where sigma is the real part of S and omega is the imaginary part of S. So what happens when we transform a differential equation from the time domain to the frequency domain using Laplace transformation? So what happens is that the differential equation gets converted, differential equation in the time domain, uh, where all variables are functions of time, gets converted into an algebraic equation in the frequency domain, algebraic equation in the frequency or the S domain, because of this transformation called the Laplace transformation. And this helps us in kind of simplifying the problems. We have already seen that network analysis problems are in general governed by differential equations, and the use of Laplace transformation helps us in converting those differential equations to algebraic equations in S and solving them in general in a more easy way. So uh, what happens is that network elements in the frequency domain get a slightly different kind of representation after Laplace transformation. So we are going to look at a couple of things in this lecture. Number one, we are going to look at a representation of standard network elements RL and C in the S domain, that is after we have transformed their governing equations uh, using the Laplace transformation. And then we are going to look at the application of standard methods in the transform domain, standard methods like mesh analysis, nodal analysis, right, etc., in the transformed domain. And the third thing, we are also going to have a brief look at the application of network theorems like the Thevenin's and the Norton's theorem in the S domain, in the transform domain. We are going to see that the overall uh, representation, the presentation of the problem in the S domain is simpler as compared to solving it in the time domain. So let us look at what we have from the time domain. So let us take the element, the resistance, and we already know that in the time domain, the governing relationship for a resistor is Vt is equal to Rit, a standard resistor constant, right? And if you apply Laplace transformation on both sides of this equation, you will get V of S is equal to R I of S. In general, in the frequency domain, the notation is of the convention is of using capital letters. So you have capital V and capital I here. So if you have to basically represent the same equation now as a circuit diagram, you will be drawing something like this. You'll be imagining a current I of S in the frequency domain flowing through a resistor R and causing a drop V of S in the frequency domain. So the basic representation remains almost the same, except that the functions now become functions of voltage and current are represented as functions of S, the complex frequency. Let us look at now uh, the inductor. So for the inductor, you already know Vt, the governing relationship, standard inductor, L dit by dt. If you transform this equation to the S domain, that is, you apply Laplace transformation on both sides, you will get something like this. Vs is equal to SL Is minus L I 0 minus. Please see the notation. The transformed equation variables are written as capital letters, whereas the initial condition, being the condition of the current at 0 minus being a constant, is written as a small uh, alphabet here, I0 minus. So if you have to basically redraw the same circuit and the same equation as a circuit, so in the time domain, you will be drawing something like this: it vt, right? And the governing equation being vt is equal to l I dash t. In the frequency domain, you have something like this: sl is vs, and this drop being li 0 minus. So you see the the equation, the circuit diagram has slightly has changed a lot in case of the inductor, right? You have a voltage source in series with the inductance, and the inductance also changes. It just does not remain L. It is now a product of the frequency and the inductance. So 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 this SL is called the impedance in the frequency domain, and the units are the units of resistance, that is ohms, because you can see that it is basically a ratio between voltage and current, right? So we have to remember this equivalent representation in the S domain for the inductor. Similarly, we can transform the other equation for the inductor, where we have it is equal to 1 by L integral 0 minus to t vt dt plus I 0 minus. This is the integral form of the equation. If we apply Laplace transformation on both the sides, we get Is is equal to 1 by L Vs. You have an S here because this is an integration, right? Plus I 0 minus by S, right? And now you can basically redraw this as a circuit, because these are currents now. So you can basically, this is as if you are applying a voltage Vs, right? And this is an admittance SL, and then you have this current Is, which is equal to Vs into 1 by SL, right? Plus this another current that you have here, I0 minus by S. So you see, this is another way of representing the inductor in the frequency domain as a combination of 1 by SL here, which is basically called an admittance because it has units of mhos, unit mho or Siemens, because it's the ratio between the current and the voltage. It's inverse of resistance. So this is the admittance equivalent circuit diagram for the inductor, where it is represented as an admittance in parallel with a current source. So basically what we are doing is we are transforming the equations to the S domain and then rewriting the equation as a circuit diagram, right? A similar methodology can be followed for the capacitor, right? Where we have IT is equal to C dVt by dt, and the standard inductor relationship where basically the capacitor relationship, where this is the current, this is the voltage drop across the capacitor, right? And if we transform this into the S domain, you get Is is equal to SC Vs minus C small v 0 minus, right? And you can basically write this again because now your uh, input is the voltage and output is the current, so you can basically write this like redraw this like this, where this is your admittance because SC would be having units of admittance. This is the voltage, so this current is going to be SCVS, and then you're subtracting a current equal to CV0 minus from here, and here is your Is. So this is SC and this is CV0 minus. So this would be the equivalent circuit diagram for the capacitance in the admittance format, right? If you use the other equation wherein you have Vt is equal to 1 by C integral 0 minus to d it dt plus v 0 minus, and transform this equation into the S domain, you get v of s equal to 1 by SC Is plus v0 minus by s. Here you see that 1 by SC is an impedance because it's the ratio between the voltage and the current. So let me write here SC is an admittance, right? And 1 by SC, which is the inverse of SC, is an impedance, right? So we can basically represent the capacitor in the frequency domain like an impedance, right, in combination. So you have a voltage source here, right, a DC voltage source, V0 minus by S. This is your Is, it gets multiplied with this impedance, and overall this is your drop Vs from this point to this point. So Vs is equal to Is into 1 by Sc plus V0 minus by S. So this is the equivalent representation of the capacitor in the S domain in the impedance form. So these representations basically 1, 2, 3, 4 for the inductance and capacitance, and 1 for the resistance, would be used to draw what we call the equivalent circuit diagrams. The equivalent circuit diagrams, in the S domain. And these equivalent circuit diagrams would then be used to solve the network analysis problem. As an example, uh, let us let us take a let us take a circuit as an illustrative example of how these transform methods are applied. Let us take a simple circuit wherein you have a DC source, right? A switch, a resistance, an inductance, and a capacitance, right? So say 3 ohms, 1 Henry, half farad, and suppose this is 5 volts. Suppose this switch S is closed at t is equal to 0, and the initial conditions are given as I 0 minus IL 0 minus, which is the inductor current, is equal to 2 amperes, and VC 0 minus, which is the capacitor voltage, is equal to 2 volts. So basically this is your inductor current IL T, and this is your capacitor voltage here VCT. So the question is, what is the overall current in the circuit after the switch has been closed? So the question is, find ILT t greater than equal to 0, right? So if we have to solve this using the transfer methods that we just redraw the circuit in the S domain. So we will redraw the circuit in the S domain, in the frequency domain, right? So we'll use either the impedance or the admittance format for the various circuit elements. In this case, since we'll be using the mesh analysis, we'll be using the impedance form. So if we redraw the circuit in the S domain, and the start with the resistor, for example, and we redraw it for t greater than equal to 0. So we close the switch, right? So the resistor remains the same. The capacitor and the inductor becomes S times this inductance. So S ohms in series with, if you look at this equivalent circuit diagram, in series with the voltage source given by Li0 minus. So in series with a voltage source given by, we are assuming a current in this direction, so this current is actually ILS, right? This is R, which is 3 ohms, and this is minus plus Li0 minus. L is 1 Henry, I0 minus is 2 amperes, so this is 2 volts, right? And then you have the capacitor here. Now the capacitor as an impedance is 1 by SC. Capacitor as an impedance is 1 by SC. So this means this is 2 by S because it's half farad. And then it has in series with it a voltage source given by V0 minus by S. So you have, now please remember the signs, they have to be correct because the current is in the downward direction. So it has to enter the positive terminal of the voltage source that you have connected to account for the initial conditions. So this is going to be V0 minus by S, which is again 2 by S here. And then this whole circuit gets closed. The voltage source 5 would become 5 by S in the S domain. If you apply Laplace transformation, this is going to be 5 by S, and this current is now actually your current ILS, which you have already shown here. So this is the equivalent circuit in the S domain for time t greater than equal to 0, right? So please notice that we don't have to actually evaluate the initial conditions for 0 plus from 0 minus when we are applying the uh, transform methods. The initial conditions are automatically taken care of, and the transition from 0 minus conditions to 0 plus conditions are automatically taken care of using the equivalent circuit diagram. So now you can apply uh, KVL in this mesh, get minus 5 by S plus 3 times ILS plus S times ILS. Now this is a voltage rise, minus 2 plus 2 by S into ILS, right? And this is again a drop, 2 by S equal to 0. So you get basically 3 plus S plus 2 by S into ILS is equal to 5 by S plus 2 minus 2 by S, right? So you can find ILS is equal to, if you simplify this, you'll get 2S plus 3 divided by S plus 1 into S plus 2, which you can apply partial fraction expansion to get 1 by S plus 1 plus 1 by S plus 2. And then you can write basically your current in the time domain as e to the power minus t, the inverse Laplace of 1 by S plus 1 plus e to the power minus 2t, the inverse Laplace of 1 by S plus 2. And straight away, after just solving an algebraic equation in S, you get the time domain solution after applying inverse Laplace transformation to the solution that you obtained from the algebraic equation, and you solve the problem quite quickly, right? So I will again repeat the procedure. The procedure is very simple. You first rewrite the circuit in the S domain, transforming all the elements. Please ensure that you transform all the elements correctly. Like for example, the voltage source is a constant, so it becomes constant divided by S in the time domain. And then you draw the admittance or the impedance equivalent of all the circuit elements, and then apply the algebraic apply the standard methods whichever you are applying, whether mesh analysis, nodal analysis, and after obtaining the solution in as a function of S, you apply inverse Laplace transformation to get the solution as a function of time. So this is how you basically apply transform methods. Now let us take one more example wherein we are applying say for example uh, Thevenin's theorem, application of Thevenin's theorem in transformed circuits. The application of Thevenin's theorem, or any other theorem for that matter, is very similar to what we have actually used it for in DC circuits, but I will still illustrate it here with an example. So let us suppose we have a circuit like say simple a current source, say for example I of t, and then you have a resistance R, an inductance L, capacitance C, right? And you are interested in finding the Thevenin's equivalent circuit between points 1 and 2. Please remember that the Thevenin's equivalent circuit in the time domain would actually keep the terminals 1 and 2 and whatever is connected in between, right? And transform everything else into a voltage source, which we called the Thevenin voltage, right? And uh, an equivalent resistance called the Thevenin resistance, right? So you should be able to get something like this. But in this case, you will not have a resistance but an equivalent impedance, right? Because you don't have just a resistance in the circuit, you also have admittance, impedances and admittances, or in the time domain you have inductance and capacitance. So how do we proceed? The process is similar to what we have done earlier. We rewrite the circuit in the S domain, the equivalent circuit in the S domain. And suppose we also have initial conditions. So you have some initial condition on the inductor current I0 minus and some initial condition on the capacitor voltage, which we call V0 minus, right? So there is an initial inductor current called I0 minus and initial inductor voltage equal to capacitor voltage equal to V0 minus. So when we draw the equivalent circuit in the S domain, again this current now becomes a function capital IS of S. The resistance remains unchanged. The inductance as an impedance is written as SL, right? In if the current we are unchanging the direction like this I1S, right? So this is now going to be a voltage source with the current entering the negative terminal Li 0 minus, and then you have here V 0 minus by S for the capacitor, and the capacitor itself, which is 1 by SC, represented as an inductance, as an impedance. And this is your terminal 1 and terminal 2. So you're looking at this voltage, right? You have to basically find out the Thevenin equivalent voltage between these two terminals and the Thevenin equivalent circuit, Thevenin equivalent resistance from these 2 points. So basically you redraw the circuit in the S domain and then apply uh, the the method that you want to apply. So how to find the Thevenin equivalent impedance? Now we call it ZTHS, not RTHS, because it's going to be an impedance. We open circuit the load terminals. So the load terminals are given here. We'll open circuit the node terminals, right? And we find the equivalent resistance, equivalent impedance between these 2 points, terminal 1 and terminal 2, right? So if you look at and you not only open the load terminals, you also short circuit the voltage sources and open circuit the current sources while looking into the circuit. So you'll have to short circuit the voltage sources. So there is a short circuit here, there is a short circuit here, right? And there is an open circuit here, so this point is open. So if you look through from this side, you just see an impedance SL plus R. Yes, because there's a short circuit like this, and an open circuit across these 2 terminals. So you just see SL plus R. So you can write down your Thevenin equivalent impedance is equal to R plus SL, right? The second thing is to find out the open circuit voltage between these 2 terminals. So you have already open circuited the 2 terminals. Now what is the open circuit voltage between these 2 terminals? So if you apply KVL in this mesh, because there is an open circuit here, so there is no current in this loop, there is no current in this loop, it's zero current, you have open circuited. So if you apply KVL in the mesh, you just have this IS current flowing through this resistance R. So you can write down minus R is plus minus Li 0 minus plus V 0 minus by S plus, so this we call VTH S plus VTH S equal to 0. So you can write down your VTH S as RIS plus Li 0 minus plus V 0 minus by S, right? So this gives you your this is minus V 0 minus by S. So basically you have transformed the above equivalent circuit into in the S domain as follows. So you have this VTHS, you have this ZTHS, and then you have these two terminals 1 and 2 which have the capacitance in between given by 1 by SC, and you have found out your VTHS to be RIS plus Li 0 minus minus V 0 minus by S, and you have found out your ZTHS to be equal to R plus SL. So if the problem is to find, for example, this current I1S, you can say that your I1S is VTH is ZTH S plus 1 by SC, right, which is equal to RIS plus Li 0 minus minus V 0 minus by S divided by R plus SL plus 1 by SC. So you basically found out the solution for the current flowing in the circuit, in this circuit, right, in the actual circuit, which is the current here in this I1T. You have found out I1S using the frequency domain methods, using the Laplace transformed equivalent circuit. And if you know the values of R, L, and you know the initial conditions 0 minus and the value of the capacitance, you can apply inverse Laplace on this, right? And inverse Laplace of I1S is going to give you I1T. So this is how you apply theorems, network theorems in transformed circuits. Same goes for any other theorem that you want to apply. The basic process is the same. Transform the equation, transform the circuit into the S domain, write down the equivalent circuit as an impedance equivalent circuit or an admittance equivalent circuit for inductances and capacitances, and then solve the algebraic equation to get the solution, and then apply inverse Laplace transformation to get the variable in the time domain. That's all. Thank you very much.